Hi everyone, and this is Hess's Law. So not all delta H values can be determined by calorimetry. So sometimes the change in temperature is too small, or it's too difficult to measure the temperature change of the surroundings. For instance, if the surroundings are a gas or it's air, and that's what's getting heated up or cooling down. So we have an alternative method to find delta H, and that is Hess's Law. So we're going to learn how to do that today. So Hess's law is the value of the delta H for any reaction that can be written in steps is equal to the sum of the values of the delta H for the individual steps. Now that's a very complex type of explanation or definition, but basically what it means is that the delta H of a target equation can be equal to known equations that add up to actually be the same as the target. So I'm going to lay down the foundation, but it's not going to make a ton of sense until we have some context, which means our first example. So stick with it. Here are the steps for Hess's law. So a target equation is going to be given, and your job is to find the delta H. You're going to have several known equations that you're going to manipulate to match the target equation. The manipulated equations will then be added up to match the target equation, and then you're going to add up the delta H's to find the delta H of the target equation. There are two different types of manipulations we can do. We can flip an equation, and when we flip it, it means the reactants become products and vice versa. If we flip an equation, we also have to flip the sign on the delta H. So a positive becomes a negative and vice versa. We can also change the coefficient in front of an ingredient by multiplying or dividing the equation by a value. So again, if we want, let's say, a 2 in front of a water molecule, I can multiply everything by 2, and then again, what I do to my equation, I must also do to my delta H. So I would multiply by the same value that I'm using to fix my equation. Again, just laying some groundwork, it'll make more sense when we try it on for size. When we're adding the equations in the last step, elements or compounds that are on the same side of the arrow will be additive, we'll add them together. Elements and compounds on opposite sides of an arrow will cancel or reduce. All right, let's give it a shot. Now, the first thing we're going to fix is just these arrows, so we should have arrows in here. And I like to have all my arrows lined up so I can very easily see left side versus right side. Now the subscripts didn't translate when I went into this program, but we'll make sure we do that when we put them into our good copy down below. So in red we have our target equation. So we have 2 C2H4Os plus 2 H2Os making 2 C2H6Os plus O2. This is an equation that we haven't been able to find the delta H value for, so our job is to take the two given equations, manipulate them, and add them together to match the target equation. If we can get the equations to cancel out to match the target, the delta H's will do the same thing, and that's my goal. I want the delta H to be solved for. So here's what I need to do. I need to look at each equation one at a time and decide what manipulations am I going to do to try to match the given equation to the target equation. So here's how we're going to start. We're going to start at given equation number 1, and I'm just going to compare what does the given equation have in common with the target equation. So if I have a look, I have this ingredient in common. What else do I have in common? I have some oxygen in common, and I also have some water in common. They have lots of common ingredients. Now, how do I choose which one to focus on to make it a match to the target here? How am I going to let this steer my information to manipulate this equation? If I have a peek at the second equation, you'll notice that there's oxygen and water in that second equation as well, but the C2H6O, there's no other opportunity to make it a match to my target except for now. So the one that I'm going to focus on is this one here, because the other smaller ingredients will generally work out in the end. But the C2H6O, I now want to make it a match to what I see here in the target equation. And this, sorry about that. So if we have a look at that C2H6O in the given equation versus the target equation, what will I have to do to the given equation to get it to match the target? Well, as you can see, it's on the wrong side of the arrow for 1. So that's what we call a flip. So I'm going to want to flip this equation so that reactants to become products. The other thing that's not a match is the target equation has to have a coefficient of 2 in front of that ingredient, and mine doesn't. So again, the second thing I'm going to want to do for a manipulation is I'm going to multiply everything by 2. Whatever I do to the equation, remember I also have to do it to the delta H. So I'm going to flip it and I'm going to multiply by 2. All right, let's have a look at the second equation. Same job as the first. I'm going to figure out what do they have in common with the target equation, and then who should I focus on in terms of determining my manipulations. So let's do this one in a slightly different color. We have a C2H4O in common. We have oxygen in common again. And we have water in common again. Again, this is the only opportunity to fix that bigger ingredient, C2H4O. So it's generally the bigger ingredient that we're going to focus on every time, and the smaller ingredients you'll find work out in the end. So this is the one I'm going to focus on here. And again, my job is to figure out, okay, what are the manipulations going to be so that it can match the target? You'll notice in this particular instance, the ingredient is on the left of the arrow where it should be. Again, my focal point is on this one here at the top. So it's already on the left-hand side of the arrow in my given equation, so I don't have to flip this equation. But you will notice I have a coefficient of 2 in the target equation and no coefficient in my given equation. So I will want to multiply that by 2 to fix the coefficient. And again, whatever I do to my equation, I also want to do to my delta H. So now I'm going to write out the manipulated equation. To start by lining up my arrows here, and I'm going to flip and multiply by 2. So my products are going to become reactants. So I will have 4 CO2 and 6 H2O. I generally don't bother to put the effort into putting states in here, although technically that's more correct. That's not really what I need to do here, so I'm just going to drop that. And then reactants become products, so I'm going to have 2C2H6O plus 6 O2s. And just like above, I have to make sure I do the same manipulation to my delta H. So flipping means change the sign, so it was originally negative, so now it's going to become a positive. And multiply by 2, that'll give us 471 kilojoules. All right, let's look at reaction number 2. I'm going to line up those arrows. This time I'm not flipping. I'm just going to multiply everything by 2. So I have 2 C2H4Os. I'm going to have 5 oxygens. So again, with the fraction there, 5 halves times 2. The 2's cancel, leaving us with 5. Or you can think of it as 2 times 5 makes 10, divided by 2 makes 5. A couple different ways to look at that one. And then 4 CO2s plus 4 waters. Again, when it comes to the delta H, I have to do the same manipulation to it. So this time multiplying by 2. So I'm going to maintain that negative since I'm not flipping it. And we'll have 1167. All right. I'm going to put a line here because it's now time to add our equations together. So adding means things that are on the same side of the arrow will add, things on opposite of the arrow will cancel. I like to do my canceling first. So I'm looking for things on both sides of the arrow that can either completely cancel or at least reduce. So let's have a look. I've got waters on both sides. I have 6 waters on the left, 4 waters on the right. I can get rid of 4 on both sides, leaving me with 2 on the left. Carbon dioxide can completely go. I've got 4 and 4. My oxygens, I've got 5 on the left and 6 on the right, so I can get rid of 5 on each side, leaving me with 1 on the right. And that's about it. So let's write down what we have left then. So on the left-hand side, I have 2 C2H4Os plus 2 waters. And I have 2 C2H6Os plus 1 O2 on the left. My job now is to figure out, have I done this? Have I actually met the target? That was the goal. Have I achieved the goal? So go out and have a look at the target equation. Let's make sure it's a match. So, looks good to me. All my coefficients are a match. All my ingredients are a match. That's good news because now it means I have figured out the delta H as well by adding them together. So if I add them up, I've got negative 696 kilojoules. And I have solved the mystery of the Hess's law. Yay! So I'm going to do a part B of this equation, and I actually need the part A, so I'm just going to write it down here for us. 2 C2H4Os plus 2 waters makes 2 C2H6Os plus O2. And the delta H is negative 696 kilojoules. Perfect. All right, let's read the second question here, the second part of the question. We want to know what would be the enthalpy of 25 grams of C2H4O in this reaction. So enthalpy, remember, is delta H. And I only have one equation for delta H. So my equation is delta H equals N delta HX. So if I'm solving for delta H, that means that on this screen, I must have enough information to solve for N and delta HX. Let's start with N, because we see here we have a number of grams, so that means I can do a mass to mole conversion. So let's start there. So I'm looking for moles here, my N value, using my 25 grams. I'm going to use my conversion factor with molar mass. I want my 1 mole on top, my molar mass on the bottom. It's about 44 grams. You're just using the formula there, 2 C's plus 4 H's plus an O. And so I'm getting 0.57 moles. All right, now to figure out the delta HX. We actually did this when we did our method 3 in representing enthalpy. If we have a look at this balanced equation, we have 2 moles of C2H4 making negative 696 kilojoules. So if we actually do a second formula here, we can rearrange. Again, this should look pretty familiar to us. We've seen this before in method 3. We can take any balanced equation and the enthalpy that goes with it, use the moles from the balanced equation, and solve for delta HX for any ingredient. So in this case, we're getting negative 348 kilojoules per mole of that ingredient. So now we can put it all together. Delta H equals 0.57 moles times negative 348 kilojoules per mole. You'll notice that the moles will cancel here, leaving us with negative 2.0 times 10 to the 2 kilojoules, bringing it back to 2 significant digits. All right, let's try example number 2 here. So again, same deal. I have a target equation in red. I'm just going to throw in some arrows here. And this time I have 3, oh, I have a Gingy trying to get in the closet. I have 3 known equations, so the same rule applies, even though it's a little more complex. I'm still going to do the same job. So I'm still going to look at one equation at a time, match the ingredients, and then decide what my manipulation should be. All right, starting with given equation number 1, let's see what it has in common with the target equation. So if I have a look, I think the only thing it has in common is we've got some oxygen and we've got some NO2, no N2s. Again, if I have a quick scan of the other equations, I do have another opportunity to match my O2s in the second equation, and I don't have any other options for NO2. So NO2, this is my only chance to make sure it's a match. So I'm going to focus on my NO2 here. Let me just make that circle around that 2 there. There we go. So let's focus on the NO2s and make that the focal point of our manipulations here. So the NO2s right now are on the opposite sides of the equal sign. So this equation will have to get flipped to make it a match. And I have a coefficient of 2 needed in the target, so I will have to multiply by 2 as well. And I'm just going to write it over with the delta H just so I don't forget that I have to do it to that value as well. Remember, that's my goal, is to get a proper delta H. All right, let's have a look at the second equation. The second equation, I have some H2, I have some O2, so again, we've got some O2 in common, and we've got some water in common. Again, if I have a look at the other equations, nobody else has water, so water is going to have to be the focal point here, because it's the only chance I have to match the water. So thinking about the manipulations, again, I'm going to have to flip this one. It's not on the right side. And I need a coefficient of 2. So same manipulation as that first one, by chance. All right, let's have a look at that last one. The last one, we have N2, we have H2, N2H4. This one's easy because the only thing they have in common is that N2H4. And even easier, they're on the correct side of the equals already, and there's no coefficients needed. So I get to leave that last equation the way it is. I'm just going to put a dividing line here. And let's do our manipulations now. So each equation, I'm just going to carry out the manipulations that I stated I was going to do. So the first one, I'm flipping and multiplying by 2. I'm going to start by putting my arrow in so I can line them up. So I'm going to have 2 NO2 on the left, N2 plus 2 O2s on the right. My delta H I also have to flip, so positive becomes negative, and again, multiply by 2. All right, let's line up the arrows for number 2 here. Again, I'm flipping in times 2, so I'm going to have 2 H2Os on the left, 2 H2s plus a water on the right. Delta H equals positive 483.6. The last one, line up the arrow, no manipulation needed, so I'm just going to write it out. N2 plus 2H2 makes N2H4. Delta H equals positive 47.6 kilojoules. All right, now my favorite part where we get to cancel things out. So I'm looking for things that are the same on opposite sides of the arrow. The opposites get to cancel, remember. So I can get rid of my H2s here. They're completely equal. N2s, same thing. They can go 100%. Oxygens, they're on the same side, so we can add them together. And I think that's about it for this one. So let's see how we did. On the left, we're left with NO2, 2 of those, and 2 waters. And on the right, we're left with N2H4 and 3 oxygens. So now it's time to compare it to the target equation. And it is looking great. Fantastic. That means that we've done it correctly, and that means the delta H's should add up to the number that we need. In this case, positive 464.8 kilojoules. Ta-da! All right, let's do our part B. All right, let's just like the last example of a part B, I've just written out the balanced equation and the delta H on this slide so we can see it, because we are going to need that information. So it says, what would be the enthalpy, so that's my delta H, of 430 grams of water in the above reaction. And in this case, I've just written it below, so below reaction. So if we have a look, again, delta H, we only have one equation that solves for delta H, and that is delta H equals N delta H X. So from the equation and the word problem, I have all the pieces that I need. I'm solving for delta H, so let's start by solving for N. So moles, or N, equals my given mass, 430 grams, times my conversion factor. I want my 1 mole on top, I want my molar mass on the bottom. My molar mass is about 18 grams for water, giving us 23.9 moles approximately for our moles. Let's do a little side work for delta Hx using our equation. So in this particular formula, 2 moles of water makes positive 464. I want to know what 1 mole of water makes. So again, using the same equation, but this time solving for delta Hx, I can take my positive 464.8 divided by my 2 moles, since those two values go together according to my balanced equation, leaving me with positive 232.4 kilojoules per mole of water. Now that I've got all my pieces, let's substitute and solve. Delta H equals 23.9 moles times positive 232.4 kilojoules per mole. Moles will cancel, leaving us with 5.55 times 10 to the 3 kilojoules. That's it. Now it's time to practice. One hot tip when you're doing the homework, there are a couple of questions where you have an equation that has nothing in common with the target equation. My recommendation is to do all the other equations and leave that one to the end, and then see how it's going to fit in. It's usually used to get rid of some things when you start adding your equations together. So I would do all your manipulations for the ones you know how to do, and then see what can cancel and see what still needs to cancel, and think about how you can use that extra equation to get the cancellations to work out. So those are your trickier ones. Good luck and have fun!